May 10, 1876. Philadelphia Centennial Exhibition. The engineering specifications that European steam experts received that morning would challenge everything they believed about reliable industrial power. A 45-foot-tall American steam engine designed to operate at only 36 revolutions per minute, impossibly slow by European standards. Through the morning mist of Machinery Hall, President Grant and Emperor Dom Pedro of Brazil approached George Henry Corliss's massive creation, while thousands of international observers waited to witness either American engineering triumph or national humiliation. European slide valves required constant grinding against metal seats, wearing out every few weeks and shutting down entire factories for repairs. The British and German engineers scoffed at Corliss's revolutionary approach, separate steam valves that dropped shut using vacuum cushions instead of grinding metal. No European manufacturer believed such gentle mechanisms could handle serious industrial loads. Yet this quiet former store clerk from rural New York claimed his patient, whisper-soft valves would outlast anything Europe could build. 8,000 miles from European workshops, the most decisive reliability revolution in steam power was about to reveal itself. Not through brute force or grinding precision, but through the systematic gentleness that would redefine what American engineering could accomplish. The mechanical drawings spread across George Henry Corliss's workshop table told a story that contradicted 30 years of European steam engineering. While British and German manufacturers perfected their slide valve systems through incremental refinements, grinding metal seats smoother, machining tolerances tighter, adding more lubrication points, Corliss had reimagined the fundamental problem. His sketches revealed 4 separate valves per cylinder, each controlled by a central rotating disc he called the wrist plate, eliminating the grinding contact that destroyed conventional engines. Thomas McKnight ran his calloused fingers along the prototype valve mechanism, feeling for the microscopic imperfections that would reveal themselves under industrial loads. 30 years of machining steam engines had taught him to trust his hands more than engineering drawings. The Corliss design felt different, smoother, more deliberately balanced. Where European slide valves scraped against their seats thousands of times per hour, wearing grooves that required constant adjustment, these valves moved in precise arcs, opening with mechanical hooks and closing with cushioned dashpots that caught the falling metal like gentle hands. The engineering elegance lay in separation. European engines mixed steam and exhaust through the same valve passages, creating temperature swings that expanded and contracted metal components dozens of times per hour. Thermal stress cracked cylinder heads, warped valve seats, and loosened bearing tolerances until the entire system required shutdown for repairs. Corliss's separate steam and exhaust valves never experienced these temperature fluctuations. Steam entered through dedicated passages that remained consistently hot. Exhaust departed through separate channels that stayed uniformly cool. The metal components operated in thermal equilibrium, eliminating the expansion cycles that destroyed conventional engines. McKnight watched Corliss demonstrate the hook release mechanism that controlled steam admission. When cylinder pressure built to the predetermined level, a weighted governor tripped a curved hook, instantly releasing the steam valve. The motion resembled a pocket watch escapement, precise, repeatable, mechanical rather than frictional. No grinding, no scraping, no gradual wear that changed timing characteristics over thousands of operating hours. The valve either engaged completely or disengaged completely, with no intermediate positions that created uncertainty. The vacuum dashpot system fascinated McKnight even more. As each valve fell toward its seat, a carefully calibrated vacuum chamber slowed the descent, cushioning the final contact. The valve settled onto its seat with barely audible contact, unlike the metallic hammering of European slide valves that announced their operation throughout the factory floor. McKnight had spent decades listening to steam engines, diagnosing problems through subtle changes in their mechanical rhythm. Corliss engines operated in near silence, their only sound the steady whisper of steam moving through dedicated passages. Orders began arriving at the Corliss Steam Engine Company faster than the Providence factory could fulfill them. Mill owners from Massachusetts textile towns reported 30% fuel savings compared to their European engines. Steamship operators discovered Corliss engines maintained consistent power output regardless of sea conditions, while conventional slide valve engines lost efficiency as salt air corroded their grinding surfaces. Factory superintendents wrote testimonials describing months of continuous operation without valve adjustments, eliminating the weekly shutdowns that cost them thousands of dollars in lost production. The numbers validated Corliss's theoretical predictions with remarkable precision. European slide valve engines typically achieve 12 to 15% thermal efficiency, converting most of their coal consumption into waste heat rather than useful work. Corliss engines consistently delivered 20 to 22% efficiency by eliminating the energy losses inherent in grinding valve operation. The separate steam and exhaust passages maintained optimal temperatures throughout the operating cycle, reducing heat transfer losses that plagued conventional designs. McKnight supervised the construction of the company's largest order, a 1,200 horsepower engine for a Pittsburgh steel mill. The massive cylinders required precision boring to tolerances that challenged even his experienced machinists. Unlike European slide valve engines that accommodated manufacturing imperfections through adjustable components, Corliss engines demanded absolute accuracy in every dimension. The wrist plate mechanism could not compensate for sloppy machining or imprecise assembly. Each valve had to operate in perfect synchronization with its three companions, opening and closing with timing accuracy measured in fractions of seconds. The steel mill installation proved the design's scalability. For 6 months, the engine powered rolling mills, blast furnace blowers, and overhead cranes without interruption. European competitors waited for the inevitable breakdown that would validate their skepticism about American engineering methods. Instead, production reports showed consistent output hour after hour, day after day, with maintenance limited to oil changes and routine inspections. The separate valve design eliminated wear patterns that required European engines to shut down every few weeks for component replacement. By 1875, the Corliss Steam Engine Company employed over 500 skilled machinists in Providence, making it one of New England's largest industrial employers. European manufacturers began sending technical observers to study American methods, abandoning their public dismissal of colonial engineering in favor of private investigation. The fundamental question that had driven Corliss's innovation, how to eliminate valve wear rather than simply manage it, had produced a mechanical solution that outperformed European approaches through patient precision rather than brute force grinding. The stage was set for the ultimate validation that would determine whether American engineering innovation could prove itself before the world's most demanding industrial audience. The morning of May 10, 1876, arrived with Philadelphia wrapped in unseasonable spring fog that muffled the sounds of 10 million visitors converging on the Centennial Exhibition. President Ulysses Grant stepped from his carriage at precisely 10:45, his weathered face betraying no emotion as he surveyed the massive structure of Machinery Hall. Beside him, Emperor Dom Pedro of Brazil adjusted his formal military uniform, both men acutely aware that the next hour would either validate or humiliate American industrial ambitions before the world's most critical engineering audience. George Henry Corliss stood beside his towering creation, methodically checking brass fittings and gauge readings with the deliberate precision that had defined every aspect of the engine's construction. The machine rose 45 feet above the exhibition floor, its 56-ton flywheel motionless but radiating potential energy like a coiled spring. Steam pressure had been building in the boilers since dawn, reaching the 200 pounds per square inch required to drive. 1,400 horsepower through more than a mile of underground shafting to 800 separate machines scattered throughout the 13-acre hall. European observers clustered near the roped barriers, their conversations conducted in the confident tones of men who had witnessed countless steam engine demonstrations. Sir William Armstrong stood among the British delegation, his arms folded across his chest as he studied the Americans' mechanical arrangement with barely concealed skepticism. The engine's massive proportions contradicted every principle of efficient steam design that had powered British industry for half a century. 44-inch cylinders operating at only 36 revolutions per minute seemed primitive compared to the high-speed compact engines that drove Manchester textile mills and Birmingham metalworking shops. The ceremony began with a choir of 1,000 voices performing the specially commissioned Centennial Hymn, their harmonies echoing through the vast iron and glass cathedral of American manufacturing capability. As the final notes faded, President Grant approached the polished brass startup valve that would admit steam to the massive cylinders. His hand paused momentarily on the wheel, understanding that this single motion would either demonstrate American engineering superiority or confirm European suspicions about colonial mechanical competence. The valve opened with a gentle hiss that seemed almost anticlimactic given the enormous forces about to be unleashed. Steam flowed through carefully designed passages to the 4 separate admission valves that Corliss had spent 5 years perfecting. The wristplate mechanism began its stately rotation, engaging the mechanical hooks that would open each valve in precise sequence. Unlike the grinding cacophony that European visitors expected from high-pressure steam operation, the Corliss engine whispered to life with barely audible mechanical precision. The 56-ton flywheel began its first revolution with ponderous dignity, gathering momentum as steam pressure built in the cylinders. Power flowed through underground tunnels to leather belt systems that connected the central engine to every machine in Machinery Hall. Printing presses thundered to life, their mechanical rhythms synchronized to the engine's patient heartbeat. Textile looms began their intricate dance of warp and weft. Metalworking lathes spun to precise speeds, ready to demonstrate American manufacturing capability to international buyers who had traveled thousands of miles to witness this moment. Emperor Dom Pedro stepped forward to add ceremonial steam pressure, his action symbolizing international recognition of American industrial achievement. The additional power surge caused the flywheel to settle into its designed operating speed, the massive disc rotating with such perfect balance that visitors claimed they could hear individual conversations despite standing next to 1,400 horsepower in continuous operation. The silence spoke louder than any mechanical demonstration European engineers had previously witnessed. Thomas McKnight moved through the crowd of international observers, listening to their amazed comments as they struggled to comprehend how such enormous power could operate with whisper-quiet precision. German engineers pulled out pocket watches, timing the flywheel's rotation and calculating the mechanical advantage that delivered consistent power to distant machines through seemingly impossible transmission distances. French metallurgists examined the engine's components, searching for the superior materials that must explain its smooth operation, only to discover conventional iron and steel manufactured in American foundries using techniques they considered inferior to European methods. The true revelation came as hours passed without the mechanical degradation that characterized European steam demonstrations. British slide valve engines typically showed measurable power loss within 30 minutes of startup, as grinding surfaces wore microscopically smaller grooves that altered timing relationships. The Corliss engine maintained absolutely consistent output hour after hour, its separate steam and exhaust valves operating in thermal equilibrium that eliminated the expansion cycles destroying conventional designs. William Dean Howells, the prominent American writer, captured the international atmosphere in his dispatch to Atlantic Monthly, describing the engine as rising loftily in the center of the huge structure, an athlete of steel and iron with not a superfluous ounce of metal on it. His words reflected the growing recognition among European observers that American engineering had achieved something unprecedented, industrial power that combined massive scale with unprecedented reliability through mechanical principles that contradicted established wisdom. As afternoon shadows lengthened across Machinery Hall, the Corliss engine continued its steady operation, while European competitors privately acknowledged that their fundamental assumptions about steam power had been challenged by colonial innovation. They could no longer dismiss as primitive experimentation. The patient precision of American engineering methods had proven itself before the world's most demanding technical audience, setting the stage for the ultimate industrial test that would determine whether such gentle mechanical principles could survive the brutal demands of continuous factory operation. October winds swept across the Philadelphia Exposition grounds as George Mortimer Pullman stepped from his private railroad car. his calculating gaze already fixed on the challenge that would determine the future of American steam engineering. 6 months of flawless exhibition operation had impressed international visitors, but Pullman demanded proof that transcended ceremonial demonstrations. His expanding railroad empire required industrial power that could operate 24 hours daily, 365 days yearly, driving the machinery that manufactured luxury passenger cars worth millions of dollars annually. The Centennial Engine had charmed crowds and silenced European skeptics, but Pullman's Chicago factory would test whether gentle precision could survive the relentless demands of continuous industrial production. The financial stakes dwarfed any previous steam engine sale in American history. $100,000, equivalent to nearly $3 million in future currency, represented not merely a purchase, but a validation that would determine whether Corliss's revolutionary principles could scale from exhibition spectacle to industrial reality. European manufacturers flooded the American market with competing proposals, their sales representatives emphasizing decades of proven slide valve performance in British textile mills and German metalworking facilities. They offered immediate delivery, established maintenance networks, and the security of time-tested technology that had powered European industrial dominance for half a century. Sir William Armstrong arrived in Chicago personally to oversee the British bid, his confidence bolstered by reports from Manchester factory owners who operated hundreds of slide valve engines with predictable maintenance schedules. His technical presentation emphasized the mathematical certainty of wear patterns that allowed precise scheduling of valve replacements every 6 to 8 weeks. European engineering had mastered the management of inevitable mechanical degradation through systematic component replacement and preventive maintenance protocols that minimized unexpected shutdowns. George Henry Corliss faced the most critical decision of his career as he studied Pullman's requirements in his Providence workshop. No steam engine manufacturer had ever attempted continuous industrial operation at such scale and duration. His own engineers expressed private concerns about bearing wear under constant loading, boiler scaling from uninterrupted operation, and thermal cycling that could fatigue even the most carefully designed components. The separate valve system that had performed flawlessly during 6 months of exhibition duty would face stresses that no amount of theoretical calculation could predict with absolute certainty. Pullman's technical specifications revealed the brutal reality of continuous manufacturing operation. The engine must maintain 1,400 horsepower output while driving machinery that shaped steel car frames, operated hydraulic presses that formed decorative metalwork, and powered the precision tools that crafted the luxurious interior appointments that distinguished Pullman palace cars from ordinary railroad equipment. Any significant power fluctuation would interrupt manufacturing processes that required absolute consistency to maintain the quality standards that justified premium pricing in competitive markets. The European alternative seemed increasingly attractive as Pullman's engineers calculated the risks of unproven American technology. British slide valve engines offered the certainty of predictable failure modes and established repair procedures. Factory superintendents could schedule maintenance shutdowns during slow production periods, minimizing the impact of inevitable valve replacements on overall manufacturing output. The grinding wear that destroyed slide valve surfaces occurred gradually, providing warning signs that allowed planned component replacement before catastrophic failure disrupted factory operations. American investors began hedging their commitments to Corliss's company as European sales representatives emphasized the folly of gambling an entire manufacturing operation on unproven mechanical principles. The gentle dashpot cushioning that impressed exhibition visitors seemed inadequate for the harsh realities of industrial loading cycles that would stress every component beyond design limits. Even supporters questioned whether precision mechanisms designed for demonstration duty could withstand the thermal shock, mechanical vibration, and continuous operation that characterize serious manufacturing environments. Corliss's decision crystallized during a sleepless October night as he contemplated the fundamental question that had driven his innovation from its beginning. European manufacturers had achieved remarkable success by accepting valve wear as inevitable and developing sophisticated systems to manage mechanical degradation through scheduled replacement. Their approach treated steam engines as consumable machines that required constant attention to maintain acceptable performance levels. American innovation demanded a different philosophy, mechanical systems designed to eliminate wear rather than simply manage its consequences. The contract negotiations revealed the depth of Pullman's commitment to proving American industrial capability. He insisted on performance guarantees that exceeded any previous steam engine specifications, demanding continuous operation with maintenance limited to routine lubrication and inspection procedures. European manufacturers declined to accept such stringent reliability requirements, arguing that no steam technology could meet continuous duty specifications without regular component replacement schedules. Their refusal reflected decades of experience managing slide valve engines that required predictable maintenance interventions to prevent unexpected failures. Thomas McKnight accompanied Corliss to Chicago for the final technical discussions, his experienced eye evaluating the factory environment that would test every aspect of the separate valve design. The Pullman works operated with industrial intensity that far exceeded exhibition conditions, requiring steam power that could adapt to varying loads while maintaining absolute consistency. Machine. Shops demanded peak power for heavy cutting operations, then reduced loading for precision finishing work, creating thermal cycles that challenged even the most robust steam systems. The moment of decision arrived as Pullman reviewed the competing proposals with the methodical precision that had built his railroad empire. European manufacturers offered proven technology with established maintenance protocols and predictable operating costs. Corliss promised revolutionary reliability based on mechanical principles that eliminated traditional failure modes through engineering innovation rather than scheduled replacement. The choice would determine whether American industrial engineering could prove itself through patient precision or whether conventional European wisdom would prevail through the security of established methods. April 23, 1881, dawned cold and gray over the sprawling Pullman Palace car works as Florence Pullman stepped carefully across the factory floor, her silk dress a stark contrast to the industrial machinery that surrounded her on every side. Her father had chosen her for this ceremonial moment not merely for symbolic reasons, but because she possessed the mechanical curiosity and steady nerve required to initiate the most demanding test of American steam engineering ever attempted. The massive Corliss engine stood silent in the center of the factory, its 45-foot height dwarfing even the largest railroad car frames that would soon depend on its continuous operation for their construction. George Mortimer Pullman watched his daughter approach the brass startup valve with the same methodical attention he applied to every business decision that had built his railroad empire. 4.5 years had passed since the Centennial Exhibition, and European competitors had spent that entire period predicting the inevitable failure that would vindicate their skepticism about American mechanical principles. British engineers calculated that continuous industrial loading would stress the delicate dashpot mechanisms beyond their design limits within months. German manufacturers prepared contingency proposals for slide valve replacements when the separate steam and exhaust passages proved inadequate for sustained high-pressure operation. The startup sequence began with the gentle hiss of steam entering the carefully designed admission passages that George Henry Corliss had perfected through 5 years of theoretical calculation and practical refinement. Unlike the violent grinding that characterized European slide valve engines under full load, the wrist plate mechanism engaged each of the 4 separate valves with mechanical precision that seemed almost delicate for such enormous industrial forces. The 56-ton flywheel began its first revolution as 1,400 horsepower flowed through underground shafting to machinery that would test every assumption about continuous steam operation. Thomas McKnight stationed himself beside the engine's main bearings, his experienced ear tuned to detect the subtle changes in mechanical rhythm that would signal impending problems. 30 years of steam engine operation had taught him that bearing wear typically announced itself through microscopic changes in rotational smoothness long before visible damage occurred. European slide valve engines developed characteristic grinding sounds within hours of startup, as metal surfaces began the inevitable wear process that required scheduled shutdowns for component replacement. The Corliss engine operated with whisper-quiet precision that made diagnostic listening almost impossible. The first 24 hours passed without incident. Then the first week, Then the first month as factory production reached levels that exceeded Pullman's most optimistic projections. The separate valve design maintained absolutely consistent steam delivery regardless of varying industrial loads, powering metal-shaping presses during peak demand periods, then smoothly reducing output for precision finishing operations without the power fluctuations that plagued conventional steam systems. European observers arrived periodically to document the inevitable breakdown, only to find the engine operating with the same mechanical precision that had characterized its exhibition performance. Production statistics validated Corliss's theoretical predictions with remarkable accuracy. The Chicago factory manufactured luxury railroad cars at rates that far exceeded European railway equipment facilities, largely because the reliable steam power eliminated production interruptions caused by engine maintenance. Pullman's workforce expanded from 800 to over 4,000 employees as orders flooded in from railroad companies that demanded the quality and delivery reliability that only continuous manufacturing operation could provide. The gentle precision of American steam engineering had created industrial capacity that European slide valve technology could not match through conventional methods. European manufacturers watched their American market share erode as factory after factory converted to Corliss-type engines that promised continuous operation without scheduled maintenance shutdowns. British engineers began privately questioning the fundamental assumptions about steam valve design that had dominated their industry for decades. The grinding contact that they had accepted as inevitable seemed increasingly primitive compared to the cushioned precision that American innovation had achieved through patient mechanical refinement rather than brute force engineering. The thermal advantages of separate steam and exhaust passages became increasingly apparent as months of continuous operation revealed performance characteristics that exceeded even Corliss's original specifications. European slide valve engines lost efficiency over time as temperature cycling cracked cylinders. Heads and warped valve seats, requiring increasingly frequent adjustments to maintain acceptable power output. The Corliss engine delivered consistent performance hour after hour because its components operated in thermal equilibrium that eliminated the expansion stresses destroying conventional designs. Sir William Armstrong arrived in Chicago during the engine's 6th month of operation, his confident skepticism replaced by grudging curiosity about American methods that contradicted every principle of proven European engineering. His technical inspection revealed mechanical components that showed virtually no wear despite continuous industrial loading that would have destroyed slide valve systems within weeks. The vacuum dashpots continued to cushion valve closure with the same gentle precision that had impressed exhibition visitors, while the wrist plate mechanism maintained perfect timing relationships without the gradual degradation that characterized grinding valve systems. The financial impact transformed the Corliss Steam Engine Company into America's largest steam manufacturer, as orders arrived from every industrial center in the expanding nation. European competitors found themselves competing not merely against superior American technology, but against proven reliability that eliminated the maintenance costs and production interruptions that made their slide valve engines increasingly expensive to operate. Factory owners calculated that Corliss engines paid for their higher initial cost within months through reduced downtime and consistent power delivery that maximized manufacturing output. By the engine's first anniversary of continuous operation, European technical journals began publishing analyses that reluctantly acknowledged American engineering superiority in steam valve design. The patient precision that had seemed primitive to observers accustomed to high-speed grinding mechanisms had proven more durable than conventional wisdom suggested possible. American industrial philosophy had demonstrated that eliminating wear through mechanical innovation produced better results than managing inevitable degradation through scheduled component replacement, establishing a foundation for continuous operation that would redefine global expectations for industrial steam power reliability. The morning of March 15, 1910, arrived with the same industrial rhythm that had characterized the Pullman Palace Car Works for nearly 3 decades of continuous operation. Thomas McKnight, now 67 years old and bearing the title of chief engineer, walked slowly around the massive Corliss engine that had defined his professional life for 29 years of flawless service. His weathered hands traced the same brass fittings he had inspected thousands of times, searching for signs of wear that had never materialized despite 262,800 hours of continuous operation, a duration that exceeded the Sirt Seram. Entire working careers of men who had started as apprentices when the engine first whispered to life. The decision to decommission America's most successful steam engine had nothing to do with mechanical failure. Electrical power generation had transformed industrial manufacturing with an efficiency and flexibility that even Corliss's revolutionary design could not match. The Chicago Edison Company's new turbine generators delivered power through copper cables that eliminated the massive shafting systems, leather belts, and mechanical transmissions that had connected steam engines to factory machinery for over a century. Progress demanded the replacement of mechanical perfection with electrical convenience, regardless of the proven reliability that had made the Corliss engine legendary throughout American industry. George Mortimer Pullman had died 13 years earlier, but his successor executives approached the decommissioning with the reverence appropriate for dismantling a monument to American engineering achievement. The engine had powered the construction of over 100,000 luxury railroad cars, employed 4 generations of skilled machinists, and generated profits that exceeded $50 million during its 3 decades of service. European competitors had long since abandoned slide valve technology in favor of Corliss-type designs, acknowledging American superiority in steam engineering through the practical adoption of mechanical principles they had once dismissed as primitive colonial experimentation. The final shutdown ceremony drew engineering dignitaries from across the industrial world, including representatives from British manufacturers who had spent decades trying to duplicate the separate valve system that had revolutionized steam power reliability. Sir William Armstrong had died 5 years earlier, but his successors carried forward the grudging respect for American innovation that had replaced their initial skepticism about colonial mechanical competence. The gentle precision that had seemed inadequate for serious industrial work had proven more durable than the grinding force that European tradition had considered essential for reliable steam operation. McKnight supervised the careful documentation of every component as the disassembly process revealed the remarkable condition of mechanisms that had operated continuously since 1881. The vacuum dashpot showed virtually no wear after cushioning millions of valve closures with the same gentle precision that had impressed Centennial Exhibition visitors. The wrist plate mechanism maintained perfect timing relationships despite mechanical stresses that would have destroyed slide valve systems hundreds of times over. Original bearing surfaces remained smooth and true, requiring only routine lubrication to maintain the whisper-quiet operation that had characterized the engine throughout its extraordinary service life. The comparison with modern industrial equipment provided sobering perspective on the relationship between speed and reliability in mechanical design. Contemporary steam turbines operating at 8,000 revolutions per minute could generate more power from smaller installations, but their high-speed rotation created thermal stresses that caused catastrophic failures within hours of lubrication problems or cooling system malfunctions. The delicate balance between rotating assemblies and stationary housings allowed no tolerance for thermal expansion or mechanical misalignment that could be accommodated through slower, more patient mechanical principles. European technical journals published detailed analyses of the Corliss engine's extraordinary service record, acknowledging that American engineering philosophy had achieved something unprecedented in industrial history. 30 years of continuous operation without major mechanical failure exceeded the combined service life of dozens of slide valve engines that would have been required to provide equivalent power over the same duration. The patient precision of separate steam and exhaust valves had eliminated wear patterns that made conventional steam technology inherently temporary, creating mechanical systems designed for permanence rather than planned obsolescence. The final operating statistics validated every theoretical prediction that George Henry Corliss had made during the engine's controversial development. Fuel efficiency had remained constant throughout 3 decades of service, with thermal performance that exceeded European slide valve engines by 30% or more. Maintenance costs had been limited to routine lubrication and periodic inspection, eliminating the component replacement expenses that made conventional steam engines increasingly expensive to operate over extended periods. The elimination of grinding valve contact had produced mechanical longevity that redefined industrial expectations for steam power reliability. McKnight preserved the original engineering drawings and operational records that documented the most successful industrial experiment in American manufacturing history. Future generations of engineers would study the Corliss design not merely as historical curiosity, but as proof that mechanical principles emphasizing gentleness over force could achieve superior results through patient precision rather than brute power application. The separate valve system had demonstrated that innovation sometimes required abandoning conventional wisdom rather than refining established methods to incremental perfection. The last steam hissed from the admission valves as electrical power assumed responsibility for factory operations that had depended on mechanical precision for 3 transformative decades. Workers gathered around the silent engine with the same reverence they might show a fallen soldier, understanding that they had witnessed the end of an era in American industrial development. The gentle giant that had proven American engineering could outperform European tradition through methodical innovation rather than conventional force stood motionless for the first time since Florence Pullman had opened the startup valve 29 years earlier. Its legacy measured not in mechanical specifications, but in the thousands of skilled jobs, millions of manufactured products, and fundamental transformation of global expectations for industrial steam power that had emerged from one man's patient determination to eliminate wear rather than simply manage its inevitable consequences.